Hello and welcome to part 2 of this week's lecture on open channel flows. In this part, we are going to talk about different types of open channel flows and how we can characterize them. Okay, so similar to pipe flows, we can define different types of open channel flows. We can have laminar flow in an open channel or turbulent flow. We can also have steady or unsteady state flow. And so these are the types that we talked about in lecture 3 and 4 as well for pipe flows. But something that is more specific to open channel flows are uniform and varied flows. And for the case of varied flows, we can have two additional types. One is called rapidly varied flow, when the flow is or the change in properties are happening over a relatively short length scale, or we can have gradually varied flow when the properties are changing over a longer length scale. So here you can see, for example, in this diagram, you have a relatively uniform flow, but as you approach this drop here, you have a sudden increase in velocity over a very short period of over a very short length scale. So you have a rapidly varied flow, but the effect of this drop are also going to propagate upstream, where you have a slight increase in velocity over a larger length scale, and that is what we call gradually varied flow. Okay, we will look at these in more detail in the coming slides. So for the case of steady and unsteady flow, what it means that if the properties are time dependent or time independent. So if you're, for example, if you are moving from this open channel section from point 1 to point 2, and if, for example, your properties, let's say velocity, is actually not changing from point 1 to point 2 in time, we call it that you have a steady state flow. Okay. But if your velocity is changing from point 1 to point 2, then we call it that you have an unsteady state flow. Okay. Similarly, to pipe flows, we can also have laminar and turbulent flow. And if you remember that when you have a laminar flow, the layers or the particles of the fluid don't intermingle. They travel in a straight line. And for turbulent flow, you have quite a bit of intermixing between the particles. And we can define this transition from laminar to turbulent flow by using a number, dimensionless number that is called Reynolds number. And if you remember from previous lectures that Reynolds number for pipe flow is equal to rho Vd over mu. Rho is the density of the fluid, V is the velocity, d is the diameter of the pipe, and mu is the viscosity. Okay. And for the case of pipe, this d is the characteristic length. Characteristic length is the length of a system that defines the system. Okay, so that is the diameter of your pipe. While for the case of open channel flows, because we don't have a fixed dimension, we use another parameter or a characteristic parameter that is called hydraulic radius. Okay, so hydraulic radius is a parameter that we define for open channel flows as a characteristic parameter. And to calculate hydraulic radius, what we do, we take a ratio of the cross-sectional area or the wetted area divided by the wetted parameter. Okay, so cross-sectional wetted area is the area of the fluid or the channel that is in contact with the fluid. Okay, that is AC. And the wetted parameter is the length of the channel that is in contact with the fluid. Okay, so that is this dimension P here. But please remember that we are not considering this area that is not in contact with the fluid. Okay, we are not considering this side, we are not considering this side, and also we are not considering the top surface of the liquid. Okay, because that is not in contact with any solid surface. And so that is the P here. If you take the ratio of the two, you get hydraulic radius. Okay, and if you put the hydraulic radius in Reynolds number equation, you get the Reynolds number for open channel flow. In some books, you might also see that instead of hydraulic radius, they are also using hydraulic diameter. Okay, so hydraulic diameter is actually defined by this formulation here. Okay, that is 4 times of AC over P. And if you put the value of hydraulic radius, you will see that hydraulic diameter is 4 times of hydraulic radius. Okay, so please note that the diameter is 2 times of the radius of a pipe or a shape. But for the case of open channel flow, hydraulic diameter is actually 4 times of the hydraulic radius. Okay, so please remember that. So if you use this formulation here and plug the values of different parameters, we can define Reynolds number that for the case of laminar flow, you are in laminar flow, if your Reynolds number is below 500, it means that you have no intermixing between different layers of the fluid. And if your Reynolds number is above 2000, you are in turbulent flow. Okay, and in between you have a transitional region. And if you notice here that the values of these Reynolds numbers are much lower than the Reynolds number values for laminar and turbulent flow if you are in a pipe. So for example, if you are in a pipe, the Reynolds number for a pipe is around 2000, and if you are in a turbulent flow in a pipe, the Reynolds number is around 10,000. While for the case of open channel flows, these Reynolds numbers are much lower. Okay, and also another thing that for most of the open channel flows, you are mostly in turbulent flow. The reason being that open channels are very long or they have very large characteristic lengths. That is, they have large RH values, while they have very small viscosity, because mostly open channel flows are carrying water. So you have a small viscosity of water, but you have very large characteristic dimension, and as such, your typical Reynolds number is around 50,000. Okay, so it means that most of the flows in open channels are in turbulent flows. So in addition to laminar and turbulent flows, you can also have other types of flow that are called uniform flows. Okay, so uniform flows are if the flow depth remains constant, or it means that if your velocity, for example, from point 1 to point 2 remains constant, we call it as a uniform flow. Okay, so if you have a uniform flow, we also call your flow depth, that is y, that I define in part 1 of this lecture, that is the distance between the surface of your fluid to the bed of your channel. This normal depth also become this flow depth becomes normal depth. Okay, and we represent it yn, and what it means that we can say that your system is in uniform flow. Okay, and this yn is actually an important parameter that we need to calculate for open channel flows to understand what will be the level of the liquid in your open channel. Okay, and similar to uniform flows, we can have varied flows. Okay, so for or non-uniform flows, and these non-uniform flows are if the properties change with the flow direction. Okay, so you can have rapidly varied flows if, for example, you have change of velocity over a short distance time. That is that dy over dx is approximately 1. It means the change in y direction and the x direction are very quick. So that is why your gradient is 1. It means that you have a huge change in velocity over a short length scale. Then you can have gradually varied flow, and as I explained previously that for example here in this example, your velocity is changing from this point to this point, but the change in velocity is quite slow. Okay, and that's what we call that the dy over dx, the change in y direction with respect to x is really small, or your velocity is changing slowly with the flow, and that's what we call gradually varying flows. And these are just the different schematics of different flow types, so please have a look at it in your free time. In addition to these types that we defined already, we can also have another classification method that what we call Froude number. And before I go into detail of Froude number, let me explain what Froude number is. So in open channel flows, the driving force, or the reason that the fluid moves from one point to another point, is due to gravity. Okay. And if you, for example, have a non-disturbed fluid, or a fluid that is at rest, and you disturb it slightly, you will see that you have this ripple effect. Okay, and this ripple, or this wave, moves slowly from the center point to the outer side. Okay, and the amplitude this wave moves is what we call celerity. Okay, and that is represented by c. And from wave analysis, we know that this constant c is actually given by this equation, that is c is a square root of g, that is gravity, times the cross-sectional area or wetted area, divided by t, that is the surface width. Okay, so t is given here for this channel. For example, a is the wetted area, and if you use this, you can calculate c, that gives you the effect of gravity on the movement of this ripple. And if you take the ratio of c, that is the natural ripple effect, or the speed of the wave, to the actual velocity of the fluid, that is, for example, so you have the wave on the surface, but at the bottom or in the middle, you have the actual velocity of the fluid, that is, let's say, v, and the speed of the surface is c. So if you take the ratio of these two parameters, we get a number that is called Froude number. Okay, and this Froude number is a ratio of inertial forces divided by the gravitational forces. And this Froude number is very important in the sense that it tells us that if the fluid is going to enter in a hydraulic jump, and or what it means that if the fluid is going to rise or is going to subside. Okay, and in combination with Reynolds number, Froude number tells us if the fluid is going to be in a laminar or in a turbulent region. Okay, so how we can do that? So we can define Froude number by this formulation here, as I explained, that is the ratio of the flow velocity divided by the surface wave velocity, and that is given by this formulation here. And in this equation, d is the hydrodynamic depth, that, as I explained in lecture in this part 1 of this lecture, that is given by a over t. Okay, that is defined here. So if the value of your Froude number is less than 1, we have what we call a subcritical flow. Okay, so subcritical flow means that you have a low flow velocity, and the disturbance that the fluid has caused, for example, this wave, is not going to propagate upstream. Okay, so for example, you can see here in this case that as you are exiting this sluice gate, you have slight disturbance, and but because your velocities are quite low, this disturbance is not going to propagate upstream. Okay, it's just going to propagate downstream. While if your Froude number is much greater than 1 or is greater than 1, you have supercritical flow. It means that you have extremely high velocities, and as such, the disturbance that happens at that point is going to travel upstreams and downstreams, both directions. Okay, and the value of the Froude number dictates if you are going to have this hydraulic jump. Okay, so what is hydraulic jump? So hydraulic jump is a shock water experience when you are going from subcritical flow to a supercritical flow. Or in simplest sense, what it means that when you are exiting this sluice gate, the fluid number value dictates if the fluid is going to rise in its height. As you can see here, there is a small decrease in height, but then there is an increase in height. And the value of fluid number dictates that. Okay, so if your fluid number is approximately 1, it means that this hydraulic jump or this increase in height of this liquid will be smaller. But if your fluid number is greater than 1, this hydraulic jump will be quite high. Okay, and you can see this hydraulic jump effect. For example, if you put a plate under a faucet, and you will see that as the faucet hits the center of the plate and goes towards the corner, because there is a slight slope towards the corner, you have a slight jump of fluid. It means that the fluid is going to increase its height. While if you put the plate upside down and try to do the same thing with the faucet, you will see that there is no hydraulic jump, because there is no change in slope of the plate, and as such you have no hydraulic jump. It means that you are going from a subcritical flow to a relatively subcritical flow, but for the first case here, you are going from a subcritical flow to a supercritical flow. Okay, these are some basic definitions that how we can define fluids by using different numbers like Reynolds number and fluid number, and what it tells you that how rapidly the fluid is moving. If the Reynolds number is low and the fluid number is low, your fluid is moving slowly. If your Reynolds number is high and your fluid number is high, it means that you are moving fast and you are going to have certain effects due to this velocity. Okay. So that is all for this part, and in the next part we will derive some equations. Thank you for your time.